Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi taala wabarakatuh dan salam sejahtera. Okay, welcome back to our class Power System BEJ 20603. So today we will discuss about chapter 6, which is Industrial Power System. So in this chapter we will focus on introduction to industrial power system. Okay, and then we discuss about single line diagram. What is single line diagram? And then we discuss about impedance diagram, and then the last one we will discuss about per unit system, and then we try to apply for per unit system for the circuit analysis, or for the especially for the power system and three-phase circuit analysis. Okay, this is introduction to the industrial power system. Okay, differentiating. Okay, distinguish or differentiate the normal and abnormal condition of operation of the system are the main concern of the power system engineer. Okay, thus one must be very familiar with steady state AC circuit. Okay, particularly for three-phase circuit. Okay, previously we already discussed about three-phase circuit, which is we focus on the balanced three-phase circuit. Okay, so the main purpose of this chapter actually is number one, to introduce the single line diagram used in practice. Okay, number two, to discuss the impedance diagram, okay, used in power system analysis, and then the last one, to discuss the per unit system used to simplify the circuit analysis of various voltage levels. Okay, single line diagram. Okay, single line diagram. What is the single line diagram? Okay, it is used to portray the assemblage of the power system components to model a complete system. Okay, which is we try to simplify the complex power system, and then we can use the single line diagram to analyze the system. Okay, in power system analysis, a balanced three-phase system is always solve a single phase equivalent circuit. Okay, in the previous chapter we already discussed about balanced three-phase system. So from the balanced three-phase system we can convert to equivalent single-phase system. So from that we can use to solve the balanced three-phase system. Okay, therefore the single line diagram is used with the following characteristic. Okay, single line diagram is used with the following characteristics. Okay, number one, compose one of the three lines and a neutral return. Okay, we compose one of the three lines and a neutral return. Number two, the component parts are represented by standard symbol, which is we have a generator, we have a bus, transmission line, we have a circuit breaker. So all the components, all the major parts in power system are represented by standard symbol. So after this you can see the standard symbol that available that commonly used in the power system. Okay, number three, circuit parameters are not shown. And the last one, a transmission is represented by a single line between its two ends. Okay, sending and receiving ends. Okay, single line diagram. Okay, a set of standard symbol. Okay, for the single line diagram, we have a set of standard symbols. Okay, for example, we have a generator. Okay, this is the symbol for the generator, for example. Okay, standard symbol for electrical diagram have been published by, number one, by, we call it ANSI, or the American National Standard Institute. Number two, the Institute of Electrical and Electronics Engineers, IEEE. Okay, so we have a standard symbol for the generator, for the breaker, for the transformer and loads and so on. Okay, this is the symbol. This is all the symbol that this is the example of ANSI symbols. Okay, this is for the generator. This is for the okay, three phase Y, okay, connected to the ground. Okay, this is the field series, okay, generator or motor. Okay, next look at to the I3PE symbol. Okay, this is the symbols that provided by I3PE, so you can refer in detail. If you want to know in details about the symbols, you can refer to the Institute of Electrical and Electronics Engineers. Okay, provided all the electrical diagram. Okay, so this is the example of the single line diagram. Okay, example of the single line diagram. Okay, we have a complex system. This is all the symbols. Okay, this is the standard symbol provided by ANSI of or IEEE. So in this chapter, okay, we will focus on how to analyze the electrical power system. Basically, in the system we have a generator. This one, you have to familiar with this symbol. Okay, this one we have a generator. This one we call it generator. Okay, this one is a circuit breaker. This one is bus. Okay, this is a bus which is connected generator 1, generator 2, and the load. Okay, this one we call it load. This arrow we call it load. Okay, this one we call it a transformer. Okay, this is a primary side. This is a secondary side. This is a Y connected to ground at the primary side. At the secondary side, we have a Y connected to ground. Similarly to transformer number 2, at the primary side, we have a Y connected to the ground. At the secondary side, we have a delta connected system circuit. Okay, this one we have a load. This is a load. This is a load. This is a generator. Okay, this is the basic component in power system. Okay, for impedance diagram, okay, figure 4 represents a single line diagram. Okay, this is we call it a single line diagram. Okay, even if we have a three-phase system, we represent our system by using a single line. Okay, this is a transmission line. This is a generator connected to the transmission line via a transformer, and then connected to the generator 3, for example, this bus, and again connected to the load B, for example. Okay, it is used to draw a single phase. Okay, to draw the single phase, the single line diagram is used to draw the single phase or per phase equivalent circuit. Per phase equivalent circuit basically is three-phase system. Okay, so figure 5 shows the equivalent circuit of a single line diagram. Okay, this is an equivalent circuit of the single line diagram as shown in figure 4. The figure represents the per phase impedance diagram. Okay, previously we don't have the information of impedance of generator, of transmission line, transformer, and so on. We don't have the information of impedance. We call it a single line diagram. Okay, so this one we call it a per phase impedance diagram. Okay, we draw the main components with the impedance. Okay, this is impedance of the generator 1, for example. Okay, this is the impedance for generator 2. Okay, and then we have a load. Okay, connected at the same bus. Okay, then we have a transformer. This is the modeling of the transformer. Okay, this is the modeling of the transmission line. Okay, transmission line connected from transformer 1 to transformer 2, and then we have a transformer 2. Okay, including the impedances. Okay, load and generator 3. Okay, this one we call it impedance diagram. Okay, then we have a common point. This one we call it a neutral point or common point. Okay. Okay, clear. So from the single line diagram, so we can summarize from the single line diagram that we have a single line diagram, generator 1, generator 2, load, generator 3, load B, okay, and then transmission line. Okay, this one we call it a single line diagram of electrical power system. So we can draw the per phase impedance diagram. Okay, based on the single line diagram, we can draw the per phase impedance diagram. Okay, for example, we have a generator 1. This is a generator 1. Okay, we have a EMF. Okay, voltage source E1 connected to the impedance, its own impedance. Generator 1, generator 2, this is a load, this is the transformer, transmission line, transformer 2, load B, and generator 3. Okay, so impedance diagram. For the load study, okay, from the impedance diagram, for the load study, several simplifications are considered. Several simplifications are considered to ease the computational burden. Okay, for the load study or for the load analysis, we have that we need to do the simplification. Number one, the lagging loads is represented by resistance and inductance. Lagging load, lagging power factor load, resistance and inductance in series. Okay, the current limiting impedances are excluded, which is there is no current flow in the ground under balanced operating condition. This is number 2. Number 3, shunt admittance of the transformer is omitted because the value is relatively small. Okay, to make it easy, we simplify our system according to this point 1, 2, and 3. Okay, for the load study. Okay, next for the fault analysis. For the fault analysis, further omission could be considered as well. Okay, for the fault analysis, for the transient and so on. Okay, so resistance is neglected as the value of inductive reactance X is relatively higher as compared to R. Okay, for the fault analysis, we know that we can neglect the resistance because R is relatively small than X. So the Z equal to X. Okay. Passive load, what is the passive load? Passive load, for example, non-rotating machinery are usually neglected because the minimum impact of the total line current during for minimum impact. So we can neglect, we can ignore. Okay, so number 3, induction motors are ignored a few cycles after the fault because its current is reduced to zero swiftly after the motor is short circuit. Okay. Okay, this is the simplified impedance diagram from the previous impedance diagram. So we have E1, okay, there is no R, E2, there is no R, okay, we have only X for the transmission line, okay, we have E with the X. Okay, this simplified diagram according to this uh, simplification for the fault analysis, according to the fault analysis. Okay, this is our simplified diagram. Okay, all the information consideration are considered in the analysis. The impedance diagram is reduced to the circuit shown in the figure 6. Okay, figure 6 in this figure. However, the simplified circuit is only suitable for the fault analysis, not for the power flow. Circuit simplification give edge in terms of computational speeds at the expense of accuracy. If we want to increase the computational speed, so we can consider all the consideration, okay, here. Okay, so you can increase the computational speed. Okay, therefore the engineer has to decide between the computational speed, power available, or computational power available, and the accuracy required in the considering the circuit simplification. Okay, this is the overview of single line diagram and impedance diagram. So next, we will discuss about per unit system. What is the per unit system? Okay, this is the important part of this chapter. Okay, an interconnected power system has several different voltage levels. Okay, because we have a generator, we have a transmission line, we have a distribution line, for example. So of course we have a different voltage level for each side. Okay, so requires transformation of all impedances to a single voltage level in order to analyze the system. So the per unit system has devised such that the various physical quantities such as power, voltage, current, and impedance are expressed as a decimal fraction of base quantity. Okay, this is the per unit. Okay, the voltage level, okay, will be disappear in the system, the diagram. Okay, so reduce a power network to a system of simple impedances. So what is the advantage of the per unit system? Okay, this is the advantages of a per unit system. Number one, okay, clear idea of relative magnitude of various quantity. Okay, because we consider the same base. Okay, number two, the per unit impedance of equipment based on their own ratings fall in a narrow range regardless of the rating of the equipment. Okay, so all the rating of the equipment we convert to the standard rating, standard base. Okay, number three, the per units variable of transformer are the same regardless of whether they are referred to the primary or the secondary side. Whether we refer to the secondary or the secondary side of the transformer, so we have a per unit value. We have the same per unit value. And number four, ideal for computerized analysis and simulation of complex power system. Okay, so easy for computerized analysis and simulation, especially for complex power system problem. Okay, so the circuit law valid in per unit analysis. Any circuit law that you have studied, that we have discussed before, such as we have Ohm's law, we have KVL, we have KCL, we have Kirchhoff voltage law, Kirchhoff current law, we have a voltage divider, we have a current divider. All the laws, all the circuit analysis, all the circuit laws basically are valid in per unit system. So we can apply all this law to the per unit system. Okay, so next, so how to calculate the per unit value? Okay, the per unit value of any quantities, for example, we have a power, we have a voltage, we have a current, we have a impedance. So per unit value of any quantities is defined as quantity in per unit equal to actual value, actual quantity divided by the base value of the quantity. Okay, this is the main formula how to calculate the quantity in per unit. For example, you want to calculate voltage in per unit. So actual quantity voltage divided by base value of that voltage quantity. Okay. Okay, a minimum of 4 base quantities are required to completely define a per unit system. We have 4 base quantity. Okay, in order to define the per unit system, in order to analyze your circuit in per unit, so you must have 4 base quantities. You must have a 4 base quantity. Number one, for base quantity for apparent power, for voltage, current, and impedance. Okay, for each section. Okay, usually base apparent power. Okay, base apparent power, or we write SB. S apparent power, B actually is base, and base voltage VB are selected. Commonly for the system, we select the apparent power, base apparent power SB, and base voltage VB. Then from SB and VB, we can determine base current and base impedance, because base current IB equal to SB over square root 3 VB. This is for the three phase, because in three phase system, S equal to square root 3 V times I. VL, okay, line voltage times by line current. Okay, S equal to square root 3 V times I. So I base equal to S base divided by square root 3 V base. Okay, or Z, you can determine Z equal to V, okay, divided by square root 3 divided by IB, or ZB, you can determine ZB by VB square over SB. Okay, VB square over SB. Okay. Okay. This is the basic concept of the per unit system, how to convert actual quantity to the per unit quantity. Okay, so you need to determine base for the S, V, I, and Z. So usually we determine SB and VB. So from VB and SB, we can determine IB and ZB. That's the summary of this subtopic. Okay, next, look at the change of base. This is the important part of the per unit system. Okay, the impedance of individual generators and transformers are generally in terms of per unit quantity based on their own rating. Okay, for example, we have a generator. Okay, they provide the impedance, okay, in per unit. Okay, we see the database. Okay, the information given by the generator. So X per unit commonly based on their own rating. Similarly to the transformer. Okay, when you buy the transformer, all the information related to the impedances. Okay, sometimes they give in the per unit. Okay, that's value of that per unit system according to their own rating. So when we use all these equipment, generators and transformer in the system, so we need to change the base, okay, according to the base of the system. So the impedance of the transmission line are usually expressed by their ohmic value. Okay, this is for the transmission line. Okay, for power system analysis, all impedances must be expressed in per unit in a common system base. Common system base, which means you need to convert all the base value of the generator, transformer, and transmission line to the common system base. To accomplish this, an arbitrary base for apparent power is selected. Okay, commonly we select the base for apparent power. Okay, base for the apparent power, then voltage base, then we select the voltage base. Okay, first we need to select the base for the apparent power for the S, then we select the base for the voltage. Okay. Once a voltage base has been selected for a point in a system, the remaining voltage bases are no longer independent. Okay, so they are determined by the various transformer turn ratio. So we need to convert according to the transformer turn ratio. If you still remember, V1 over V2 equal to N1 over N2, for example. Okay. The relationship between the old and new per unit value is equal to, okay, what is the relationship between old and new per unit value? Okay, for example, you want to determine the Z new, okay, Z base new, so equal to Z old per unit times S new, S base new divided by S base old times V base old divided by V base new square. Okay, this is formula how to determine the Z per unit new. Okay, we try to convert per unit value of the equipment to the according to the common system base. So Z old, okay, this is provided by the manufacturer or datasheet. Okay, S base old, okay, base of the equipment. This is the S base new system. S base system. Okay, times V base old divided by V base new. Okay, this is the formula. Okay, so to understand the concept of change of base, so we can try this example. Okay, let's say we have example 1. So the one line diagram of a three-phase system is shown in figure 7. Okay, we have a one line three-phase power system. Select a common base. Okay, common base we need to select, let's say 100 mega volt ampere. This is a S. This is a S. And V on the generator side. Okay, V on the generator side. This is a generator side. Generator side. Okay, this is a generator side. V equal to V base equal to 22 kilovolt. Okay, this is the base value, common base of the system. Okay, so you have to understand this is a common base. Okay, draw an impedance diagram. So you need to draw the impedance diagram. This is a single line diagram. This one we call it single line diagram. So from this single line diagram, you need to draw the impedance diagram. Impedance diagram with all impedances including, okay, the load impedance marks in the per unit. Okay, so you need to put all the information of impedances in per unit. So the manufacturer data for each device is given as follows. Okay, this is a manufacturer data. Okay, this is a generator. So the rating of the generator is 90 megavolt ampere. Voltage rating equal to 22 kilovolt. This is a generator. Okay, with X reactance per unit. This is per unit. This per unit value equal to 18%. 18% means 0.18 per unit. 0.818 per unit. This 0.18 per unit basically is based on the 22 kilovolt and 90 megavolt ampere. Okay, so in order to draw the impedance diagram, you need to convert all this per unit value to the common base, 100 MVA and 20 volt, 22 kilovolt. Okay, this is the information of T1, transformer 1. This is a transformer 1. Okay, transformer 2. Okay, X per unit is given. Transformer 3, KS, V ratio, and X per unit of transformer 3 is given. Similarly to the transformer 4. So we have one motor. This is motor. Okay, this is a motor. S, voltage, and X per unit. Okay, the three-phase load at the bus 4. Where is a bus 4? This is a bus 4. Absorb. Okay, load. Where is load? This is a load. Okay, load absorb 57 megavolt ampere. 0.6 power factor lagging. Okay, loads absorb 57 MVA, 0.6 power factor lagging at 10.45 kilovolt. Okay, this is a voltage. Okay, which is equal to the secondary voltage of the transformer. Equal to the, this is a motor. Voltage rating of the motor 10.45. Okay, load voltage. Okay, line 1 and line 2 have reactance. This is a line 1 and line 2 reactance 48.4 and 65.43 ohms respectively. Reactance means X. So in order to answer all this question, first of all, make sure you draw the equivalent circuit. You draw the circuit and then you put all the information given in the question, and then you need to sketch, you need to draw the circuit and put all the information in the circuit. Okay, so next what you need to do, next, first you need to determine the base voltage for all section. base voltage. Okay, base voltage for all section. Okay, this is a section number 1, for example. So what is the base voltage? Is given, which is equal to 22 kilovolt. So this we call it VB1 equal to 22 kilovolt. Okay, this is a VB1. This is a section 2, section 3, section 4, okay, section 5, okay, section 6. Okay, so VB2, V base 2, okay, at the secondary side of the transformer 1, secondary side of the transformer 1 equal to the voltage at the primary side of the transformer 2. So that's why we call it, we write VB2 equal to VB3 equal to 22. We transfer to the secondary side by using turn ratio. Okay, turn ratio of the transformer. I still remember the turn ratio of the transformer. V1 over V2 equal to N1 over N2. This is the turn ratio of the transformer. If you still remember, V1 over V2. In this case, VB2 at the secondary side. So we have a V2 equal to N2 over N1 times by V1. Okay, this is a V2 equal to V1 times N2. This is a N2 because N2 equal to V2 of the transformer. So by using this turn ratio, so equal to 220 kilovolt. Okay, similarly to this one, okay, before, okay, at the secondary side we have 220. By using this turn ratio, so voltage base at the at this section equal to 11 kilovolt. Okay, at this section 5 and section 6, we have a same voltage level, which is 22 transferred to the secondary side times 110 divided by 22, so equal to 110. Okay, equal to 110. Okay, first we need to determine the base voltage for all the section. Okay, this section basically is separated by the transformer, because transformer we have a different voltage level according to the turn ratio. Okay, number 2, you need to change the base of the per unit reactance, okay, of the transformer to the 100 MVA, okay, to the common base. This is 100 MVA basically is common base, okay, apparent as common base by using this formula. Okay, change of the base. Okay, Z per unit new equal to Z per unit old times S base new divided by S base old times V base old divided by V base new square. Okay, so ZO of the transformer, okay, let's say for the transformer 1, okay, for the, okay, change the base for the per unit reactance, okay, of the generator. Okay, for the generator, sorry, we have a generator and transformer 1. Okay, for the generator, what is the value of the xg of the generator? Okay, generator, look at to the manufacturer data. Okay, generator we have a x, okay, equal to 18% or equal to 0.18. Okay, so we convert to the common base, 0.18 times, okay, S base new equal to 100 mega VA divided by 90 mega VA. This 90 mega VA, this is a old, okay, old S old. This is a S old, okay, old base, old base value of the generator 90 megawatt. Okay, so times V base old divided by V base new. In this case, V base old equal to V base new, which is 22 kilovolt. 22 kilovolt divided by 20 kilovolt equal to 1. 1 square equal to 1. Okay, so that's why we didn't write here. Okay, so equal to 0.2 per unit. So X transformer 1 equal to 0.1. Okay, by using this formula times 100. Okay, S base new divided by S base old 50. Why 50? According to the manufacturer datasheet. Okay, 50. Okay, this 50 equal to S base old. Okay, so XT1. Okay, by using the same approach, same formula, you can determine XT2. You can determine XT2, XT2, XT3, and then XT4 for transformer 2, okay, transformer 3, and transformer 4. Okay, we change the base for the per unit reactance of the generator and transformer to the common system base, which is 100 MVA. Okay, so next, change the base for per unit reactance of the motor of the load, okay, to the 100 MVA and 11 kilovolt. Okay, by using the same formula, Z PU per unit ohm is given from the datasheet of the motor. Okay, datasheet of the motor. This is the Z per unit ohm of the motor. It's given. This is the base, S base. Okay. Okay. S base new equal to 100. Okay. S base old equal to 66.5. Okay, from the manufacturer datasheet. V base old equal to 10.45 according to the datasheet. S base new equal to 11. Okay, we already calculate here 11 because base voltage at the bus 4 equal to 11 kilovolt. Okay, already calculate. So from this equation, so we can determine the new per unit of the motor equal to 0.25 per unit. Okay. Then you need to determine the impedance base of line 1 and line 2. Okay, line 1 and line 2. Line 1 and line 2, we have a S base and V base. This is a V base. We already calculate V base equal to this number for line 1 and line 2. So for the line 1, okay, V base equal to 220 kilovolt. So S base equal to 100 mega MVA, 100 MVA. So Z base equal to this formula, yeah. Okay, because S equal to V square over Z. So Z equal to V square over S. Okay, if you want to determine Z base equal to V base square over S base. So in this case, V base square equal to 220 kilo square divided by S base equal to 100 MVA. Okay, similarly to Z base of the line 2 equal to 110 K square divided by 100 MVA. So you get this value. Okay, is it clear? Okay, how to determine the impedance, okay, per unit. How to determine the impedance base. Okay, impedance base. Okay, so next what you need to do, determine the line 1 and line 2 per unit. Okay, once you have a base value for the line 1, this is the base value for the line 1, and this is the base value for the line 2. So you can determine the per unit value. Okay, impedance of line 1 per unit value of line 1 and line 2. Okay, so x1 equal to real value divided by base value. where you can get the value, the real value, the actual value. Actual value basically is come from the question. Okay, this is a value of the transmission line 1. Reactance equal to 48.4. Transmission line 2, 65.43 ohms. Okay, so per unit value for transmission line 1 equal to actual value divided by base value. This is the base value, already calculate base value transmission line 1. So you get the per unit value of x1. Okay, per unit value for x2 equal to actual divided by base. So you get this value. Okay, this is the Z base 2, 1 to 1 ohms. Okay, then the load apparent power at 0.6 power factor lagging. So from this information, we have apparent power is given from the question. So complex power for 3 phase equal to 57 angle 53.13. Okay, inverse cos 0.6. Laggings means positive. Okay, positive angle. Okay, so you got the value of the complex power. Okay, so from that you can determine the impedance. Okay, we have a S, and then we have a voltage. So from this S, complex power, and voltage, we can determine impedance, because Z equal to V line to line square over ZL conjugate. Okay, you still remember in three-phase analysis? So Z equal to VL square divided by SL conjugate. Okay, because S conjugate, S three-phase conjugate equal to V square divided by Z. Okay, so you can determine the ZL. Okay, Z load. Okay, this is the Z of the load. Okay, then the load impedance in per unit. Okay, load impedance in per unit. So what is the base? Base for the Z base for this section equal to V square divided by S base. V square is the voltage here. Voltage base here actually is equal to 11 kV. We already calculate before. Okay, we already calculate this one. V base at the section 4 equal to 11 kV. So Z base equal to 11 kilovolt square divided by 100 MVA. Okay, Z base. So from once you have a base value, you can determine ZL per unit. Okay, actual value divided by base value. Okay, this is your actual value. Okay, then divided by base value. Okay, so you got the value of ZL per unit. ZL per unit. Okay, quantity in per unit equal to actual quantity divided by base value of quantity. So once you already calculate the per unit value for all impedances, then you can draw the per unit equivalent circuit. Okay, you can draw the per unit equivalent circuits. We call it per unit impedance diagram. Okay, you have a common here, and then you have a generator connected to the transmission line. Okay, you have a transformer. You have a impedance of the transformer. This J0.2 basically equal to per unit value. Okay, not ohms value. Per unit value J0.2. This is the per unit value of the transmission line, of the transformer. Okay, this is a per unit of the transmission line. This is a per unit for the transformer. Okay, transformer. This is a load. Okay, this is your motor. Okay, this one we call it per unit impedance diagram. So you need to draw the per unit impedance diagram, and then you need to put all the information of the impedances in per unit value. Okay, this is the solution for example 1. Okay, next we look at to the example number 2. Okay, we have the motor of example number 1 operates at full load 0.8 power factor leading. Let's say the motor in, we have a motor, we have motor in the previous example operate at 0.8 leading power factor. For example, at terminal voltage of 10.45 kilovolt. Okay, so question number 1, determine the voltage of the voltage at the generator bus 1. Okay, let's say we have this condition. The question asks to determine the voltage at bus 1, V1. Okay, bus 1. What is the value of this voltage if we have a motor operate at 0.8 power factor leading at terminal 10.45 kilovolt? This is the terminal voltage. Okay, this is the circuit of the previous of the example 1. Okay, number 2, determine the generator and the motor internal EMF. EMF. Okay, so you need to calculate the generator and motor internal EMF. Okay, let's we try to answer question number A. Okay, question 2A. Okay, make sure you draw the equivalent circuit. And then you convert to the per unit. We already convert to the per unit to the per unit value. Okay, so the per unit voltage at bus 4. Where is the bus 4? This is the bus 4. Per unit voltage at the bus 4 taken as a reference. Okay, we consider this one as a reference. So V4 equal to actual value equal to 10.45 kilovolt divided by base value equal to 11. We already calculate in the previous example. Okay, value equal to 11. So this 11 equal to voltage at the bus 4 as a reference. Okay, so we got V4 in per unit. Okay, V4 in per unit. So the motor apparent power 0.8 leading power factor is given by, we have a motor. Okay, then we need to divide it by S base equal to 100 mega. So angle equal to negative. Why negative? Because we have a leading power factor. Minus inverse cos 0.8. Okay, you got apparent power in per unit. Okay, in per unit. This is the real actual value divided the base value. Okay, so we got the per unit value for the apparent power for the motor. And then calculate the current drawn by the motor. How much current drawn by the motor? Because we know that S equal to VI conjugate. Okay, if you still remember, we have a S, we have a voltage, we can determine current because S conjugate divided by V conjugate. Because we have a general equation, V equal to V, S equal to VI conjugate. Okay, so in order to determine current, I equal to S conjugate divided by V conjugate for the motor. We have a S, we have a V, so we can determine current. We can determine current for the motor. Where is the current for the motor? This is the IM. This is the IM. Okay. Next, current drawn by the load. Okay, current to the load. Okay, we have a voltage, we have Z, then you can determine current. Okay, this is a motor, this is a load in parallel. What is the value of voltage? Voltage, we already calculate the voltage in per unit at bus 4. okay, equal to the voltage across load. So in order to determine IL, current to the load, equal to V4 divided by ZL. V4 VL divided by ZL. In this case, V voltage across load equal to V4 divided by ZL. So you got the current in per unit. You got this current IL. Okay, so we already calculate IM. So we got IL. So what is the total current drawn from the bus 4? How much current? Okay, drawn from the bus 4, which is equal to summation of IM plus IL. Okay, look at to this figure. IM plus IM. This is a total current equal to IL plus IM from the circuit. Okay, you got this value. So the main purpose actually you want to determine V1, voltage at the bus 1. In order to determine voltage at the bus 1, you need to determine current at the load. Okay, current at the motor and the current at the load. And then you can determine the total current. This one you can determine the total impedance of the transmission line and transformer. This one in series. Okay, let's say this one Z1, this is a Z2, and then you parallel. Okay, to determine the equivalent reactance of parallel branches. Okay, total impedance in parallel. So this one 0.45 J, this one J 0.9. So in parallel you got 0.3 per unit. This is the X, reactance in parallel equal to 0.3 per unit, reactance X. Okay, this is X. So Z equal to JX. ZL equal to JX. So the generator terminal, okay, so in order to determine generator terminal, you can analyze according to the KVL. This KVL. Okay, you have a current here, you have a voltage here, then you can determine V1. V1 equal to, this is a V4. You have a V4. We have a V4. We already calculate V4. We already calculate V4. We have a Z line to line. Okay, this we have a this Z, and then we have a current, total current of IM plus IL. So you can determine V1. So this is your V1. Okay, we have a V4 plus Z line to line. Okay, parallel, and then times with I, total current. Okay, equal to this value, this per unit value. Okay, this is a per unit value. Okay, equal to 1 angle 15.91 per unit. So the question is how to convert to the real value from per unit. Because per unit equal to actual divided, okay, what is the meaning of per unit? Per unit equal to actual, I just write AC, actual divided by base. Base. Okay, actual value, let's say, of the voltage, actual divided by base of the voltage. This is a per unit. So in order to determine actual, you need to times between per unit value and base value. In this case, base value equal to, at this point, is the base value equal to 22 kilovolt. Okay, this is the base value for this point. Base value, okay, close to the bus 1 equal to 22 kilovolt. That's why we base at bus 1 we have a 22 kilovolt. So actual value equal to per unit value times V base equal to 22 kilovolt. So you times between per unit and base value, you will got this value. Okay, is it clear? So make sure you try to use your own calculator to determine per unit value and actual value. Okay, so this is question number 1. Okay, the question asks you to determine voltage at the bus 1. So you already calculate voltage at the bus 1. This is the real value. First of all, you calculate the per unit value, then you convert to the real value. Okay, next question number B. Question 2B. Okay, determine the generator and the motor internal EMF. Where is the internal EMF? This is the internal of this is the internal EMF of the generator. This is the internal EMF of the motor. Okay. Now you have a V1, you have a V4, you have current and so on. So you can determine this EG and EM by using the Kirchhoff voltage law. By using Kirchhoff voltage law. For example, you need to determine the generator internal EMF. Okay, you can use this loop from this point, common point, to the this point, this voltage, because we have a V1. So EG equal to V1 plus ZG times I times total current, because total current here, I capital I, equal to IM plus IL. Okay, same by using KVL. Okay, so V1, you already calculate V1, you have a ZG and then you have a I, so you can determine EG in per unit. So from the per unit, you can convert to the actual value. Okay, you need how to convert to the actual value? You need to times with V base. You need to time with V base. You need to time with V base. Okay, you need to time with V base. Okay, similarly to this one, okay, V4 minus Z motor. Okay, look at to this circuit. V4 minus Z motor equal to Vm. So Vm equal to V4 minus Z motor times I motor, Im. Okay, just apply the Kirchhoff voltage law at this point. Okay, from V4 to this point. Okay, this is a neutral point equal to 0. Okay, so you got the value in per unit. So from per unit, you can times with V base. You can times with V base at this point. V base at this point equal to 11 kilovolt. 11 kilovolt. V base at this bus equal to 22 kilovolt from the circuit. Okay, so you already, so you have to calculate EG and EM. Okay, I think that's all for today. How to use per unit system in order to analyze the power system. Okay, so from the per unit value, you can apply any circuit law, Kirchhoff voltage law, Kirchhoff current law. Maybe you can apply divider and so on in order to analyze your circuit. So by using the per unit, so after you got the value or your final answer in per unit, then you can transfer to the actual or real value. Okay, times with the base. Okay, if you calculate the voltage, you can times the per unit value of the voltage to the V base. Okay, so I hope you can understand on how to apply the per unit in the power system circuit analysis. Okay, so next you can try the exercise. You can try the exercise. We have a tutorial 1, tutorial 2, and tutorial 3. So you can try all the exercise or tutorial that available in your lecture slide. I think that's all for today for chapter 6. Okay. Assalamualaikum warahmatullahi wabarakatuh.